I know that his computer blue screened. I'm getting actually a new computer myself. Well, not new, it's a used one, but a little bit more powerful. So welcome everybody. This is our every Saturday morning. Now it's our Saturday morning chat, but it's on YouTube and Facebook. The idea is we can attract more people. I think YouTube now we have 400 and let me check my watch. Oh man, not used to all this equipment. This way you don't have feedback when we talk. Let's see. I think we have, check on the 400 and some now, I believe. So 470 keeps going up. A couple years ago, it was only about 100 and some. So that's the idea. I hope you can hear me. There is a chat here. If you haven't been here before, let me put up some links. You can, of course, go to facebook.naturalphilosophy.org or youtube.naturalphilosophy.org, and you should see, in fact, that we are live. I'm hoping someone can tell me that this is live, that you can hear me and everything. Let me make sure. Yeah, it looks like it. Yeti, my Yeti microphone. Okay, I just tested it, so that looks good. Anyways, hopefully we'll have Franklin here because he's really the guy to do this. I happen to be available today, and been working on my YouTube channel as well. Hopefully this will be able to use this as well on my YouTube. But if you're interested in joining us, if you're watching this on Facebook, you can actually join in. I will get that up for you. Let me show you. You can go to live.naturalphilosophy.org and I can put you in, and you can do it from a phone. You can do it from your laptop. You can do it from your desktop, a tablet. It's a new system called, I can show you here. There it is, live stream with live with StreamYard, a service that we're now using. So something that is new to us, but hopefully, like I said, Franklin will be here, and I can check on here to see if we're actually live. Bear with me. Oh wow, Facebook is downloading a new version. Let me see if we're live on YouTube. And if you're on YouTube watching, you can actually send us a comment. And that's something you can do. And the comment will come up to us and we'll talk about it. But we're going to look at headlines today. And those headlines are going to be coming from Google. Google has a physics page. So if you go to news.google.com, you click on science, then you click on physics. We're going to be taking a look at some of those there. Now, again, we're waiting for Franklin, who is our regular host, but I'm filling in until that happens. But that's the way these things go. New technology, new glitches and gloaches. So last week he was on here, no problem. Let me check here. Yep, and we are live. So that's good. Thank you for watching. If you want to send a comment, oh, we do have him. There he is. Yes, you are live. Great to see you. In fact, just go to show you there. Look at that. Put your comments up there. If you do put comments on YouTube, in fact, we can put them up for you. But we're going to be trying to go and talk about the headlines today. Again, I'm filling in for Franklin Hugh, who is hopefully coming by and on soon. So, and again, if you do want to join us and discuss something with me, you have something you want to talk with us at the CMPS here, we can, in fact, do so. Yep, we are live. I am checking that too, which is really great. I haven't checked Facebook, so Facebook was downloading on my phone. So let me check that out, make sure we're also on Facebook going live. Let's see if we even have a message, but hopefully it should be. Go to the John Chappell. There it is. And click on that. We're going to see here if we are in fact going live on Facebook as well. And it does look like that too. So that's pretty darn cool. Again, we used Fuse, which was really nice, but it didn't get us into the live streaming. So we're now wanting to do that, open up our avenues. It's hard to talk and manipulate and move here, but really great to see you. And I see we have people on Facebook as well. And again, if you're on Facebook and you're watching, please send us a hello or whatever. Say you're out there and you have any questions. But we're going to be going. I see Franklin is starting to come up. He plays Kilroy though. Hold on. Let's get Kilroy. I'm going to call him Kilroy because his head's always at the bottom. See, look at this. Well framed, well lit. Got my own, well, I can't show it to you, but you can see it in there. See those lights in my eyes? There we go. So let me join him up here. Okay. Hey, there he is. I'm not hearing you. Oh, okay.
Just a second.
I'm hearing
you hear me okay now?
Yeah, sounds a little trebly, but it seems to be okay. But that's okay. Yeah, absolutely. So you blue screened on us, huh?
Yeah, I have not seen the blue screen of death for years.
Oh my gosh.
But as soon as I went to try and start the broadcast, it just died on me. So
yeah,
it takes about 10 minutes to wait for
I know.
Go through its whole thing and then get back in here. So, but glad you were able to start the
no problem
the conference here.
Yeah, I know. Did you come in as yourself, or are you seeing the broadcast studio?
I think I'm seeing the broadcast studio because I can see you. So do we both have control? So can I?
Oh no! Right below there should be.
So I can. I don't know. I have some controls here.
Oh my gosh, you do. So that means what's really good about that means that. Yeah. Okay, that's much better. Right. Don't get that Franklin off the screen there. No. But that's cool. That's really good. What that means is you and I are both admins or controllers of it. So. That's pretty nifty, in fact. So if you do log in as the main guy, let's get back to you. What are you talking about? Come on, there you go. As long as you log in the main guy, I guess we can do that. So what happens is, though, of course, this is all through a browser. Google browser is best because I believe, but what it does is it uses a browser. Actually, even for the video now, I don't know if people know, but Google has a built-in video streaming now, and I don't know if it's taking advantage of it, but I think that's what's happening. The thing is, though, of course, when we get lots of people, right now we don't have as many people live, only us two. If you are interested, like I said, in coming in, how this works, how stream, what's it called, StreamYard works. Yeah, how StreamYard works is that we're allowed up to 10 people sitting in below us that we can put up on screen, an ad. We can only put 6 up simultaneously. But of course, what happens is if you're not planning to talk with us, I would please ask you to stay and only go directly to YouTube, again, to youtube.naturalvelocity.org or Facebook, because if you're just sitting there watching and you really aren't going to participate, you're going to build both Franklin and I's computers get pretty well saturated, and the CPU goes nuts, and we could end up crashing. That did happen to me that last week. In fact, I ordered a new used computer, a used one, but it's going to have an SSD drive and be a higher processor than I have now. So anyways, we have young Einstein has come in. Did you see that, Franklin?
Yeah, so I would suggest, because there isn't any kind of like flag like in Fuse to indicate that you want to talk. So I would suggest that if you want to talk, that you like send us a chat or you turn on your video, but otherwise leave your video off. So if your video is off, I think we will presume that you're there in the wings, but that you don't want to talk. But if you do want to talk, then please turn on your video, and then we will see that, and then we will put you on the screen. How about that? Is that a good standard, David?
Oh man, you're the best, man. I came on last week and I was trying to run the show in a new software. I was rambling on. You were very good at this. You've been doing this for 2 years. I've come in and watched you handle the situation, because it's not easy when you've got very strong-willed people. And even in this case, we have people from the past, people who are dead, who are coming in. Young Einstein is here with us. So, yeah, I think that's a great idea, because that keeps the CPUs on our machines down, the rate. Like I said, next Monday, I should be getting a new one, and hopefully that will make this easier. But I think what we can do is to try, since we're go ahead.
Have you seen the chat? So Bob Gray is here, and
yeah, I have seen that.
He has a presentation today, if interested.
Oh, great. That's super. So what I can do is let's get it. I'm going to bring myself down and have you up, and I'm going to have you just go ahead and do this. I'm imagining you should be able to continue this even if I get out. So that's what I'm going to do. And one of the things is too, I don't even know if a person who comes in now, and I apologize for taking a little bit of time, folks. We're still getting used to it. But wasn't it the case, Franklin, that when you were in last time, you could still share a screen even though you weren't the admin or the?
Yeah, I believe so. As soon as you put them up, they have the share screen ability.
Okay. So what we'll do then is this. I will bring myself out, turn off my video and microphone, and then you can work with Bob. I think, Bob, Bob Gray, if you can turn your video on, I'm going to get out of here and turn it off, and I'll let it go with you there, okay? Well, we've got somebody. Look at this. Look at this. Look at this. Do you read that?
We've got some people from Iceland. Welcome.
Yeah, and I am a linguist. I don't know, a lot of people know that, but Rainier, I'm a linguist, got my master's degree in linguistics, and I know that Icelandic is one of the hardest languages on planet Earth to speak. Finnish, Icelandic. If you can speak Icelandic, you are like the top of your field. They even so I really appreciate it. So there you go. We know now that Facebook is working, and we welcome people from around the world. That's the idea. So I'm going to get out of here, Franklin. You're familiar with the controls, then you played around with those a little bit.
Yeah, but like I said, stick around. I mean, Bob might be having some technical difficulties, so
okay.
We'll see. Looks like Bob has got his microphone on, so we're going to at the very least put him on. Okay, Bob.
Hello?
We can hear you, Bob.
Oh, good.
Do you have a video?
I have a camera. Share screen. How about that? Share screen.
Yeah, you can do a share screen. So what do you have for us today?
Do not show tips. Well, let's see. You'll share screen. I'm still not seeing how to figure this out.
That you would like to present on?
Well, I've been able to use the scientific literature, experimental results to prove that Maxwell's electrodynamics is not correct. So this is not a theoretical proof, but an experimental proof. And I've done up 5 slides or so, 5 or 6 slides on this, and love to present it if I can figure out how to use the system.
Well, have you clicked on the share screen button? And it should say,
yes. Will you allow StreamYard to see your screen? So it should allow, and it does nothing. Let me see.
Yeah, we're not seeing anything either.
Firefox screen, yes, entire screen. How about that? Allow. Now let's see. So I think you ought to be able to see my screen now.
No, we're not able to see your screen now, I don't think.
Let's see. Your camera and microphone are being shared. Click to control sharing. Let's see. Connection block permission, use camera, use my share the screen, allow temporary. Yes, yes, yes.
Okay, now we are beginning to see your screen there.
You may need to reload the page. I don't want to.
Well, let's see. Well, it was there briefly, and then it disappeared. So,
Remove from stream. Everyone can see and hear you.
let me see here. Now, do I need to do something special to do a screen share?
This is weird. Yeah, let's see.
I did just briefly see your screen for just
All right, let's go back here.
Now, you can send me your presentation by email, and I could share it.
Okay, I can do that. Inbox. I can go to, say, new. Let's see.
So welcome to all our new viewers. And we're just kind of working through the technical glitches here. Not quite sure why Bob's not able to share his screen there.
Let's see. Let's go to physics. Disproof of Maxwell. Open. It's attached. I click on send, and it is being sent to Franklin.
Okay. Now, hopefully my screen share works. Let's see here. If I say share screen. Let's say share that, I guess. So you see my mail.com?
I do.
That's what I'm sharing. Okay. We'll share something a little bit more interesting later. Okay. Let's see. So I can stop sharing. So that works for me. So now I just have to wait to get your email here, which should have been, okay, one new message, hopefully. Presentation. Got that. Download that. So you're going to disprove the master, huh?
Well, I've done that years ago. And only now have I figured out that in the literature there are a couple of experimentations that also disprove Maxwell. They don't realize, apparently, that their experimental results actually do disprove Maxwell.
Are you talking about his equations per se?
Well, Maxwell has a system for electrodynamics consisting of 4 differential equations and some other equations. And
well, wasn't it really Maxwell's equations? Because, curiously enough, Maxwell's equations has all bunch of other people's names on them.
Yep.
You know? And it's like, why do they call them Maxwell's equations? They're not even his equations.
Yep, I know.
So what's up with that?
You got to know the right people, I guess.
Why did he get all the credit? I mean, that's just, I don't know why he got all the credit. And then they keep on doing like really weird things with his equations, like equating apples to oranges and coming up with like the electromagnetic wave equation and crazy stuff like that. But let's see here. I think though I'm ready. Let's see here. Okay, so I think there is your presentation. Now I can't exactly see what's going on here, but I'm going to go full screen on the slideshow here. Okay, so you see that?
It's not full screen. I still see on the left all the slides in a column.
Oh, you still see all the slides on the column there, huh? Well, we may have, let's see, if I change it, then do you see it changing?
Still slide 1.
Still slide 1? Let me give it a second here. Still slide 1?
Still slide 1. You can click on the left on slide 2, see if it will go that way.
Well, I can see it switch. Let's see here. What do I see? What do I see? Yeah, that didn't seem to switch. Let me try something else. Let's try and just share my whole screen here. My entire screen I'm going to share. And what I'm going to do is I'm going to put up just my, so I'm going to, first of all, I'm just going to put up just my setup.
Yep, I can see you.
And now I'm going to try and share my entire screen and see whether that's going to work. So I click on entire screen, and then it doesn't, like you were saying, it doesn't seem to do anything. Or maybe it's just slow. Or maybe my computer's about to crash. So
we see your camera, but we don't see any of your laptop screen.
Yeah, we don't, because it seems to be a little bit stuck there. Okay, so that didn't seem to work. Let me turn off my camera as well so I can reduce.
Oh, there's something.
I'm going to reduce my bandwidth, and now I'm going to click your entire screen, application window. I'm going to share the application window. Okay, so what do you see there?
Screen. I can see the second slide.
Okay, I'm going to try and switch to the third slide. Do you see it switching?
No, second slide.
Still the second slide. So it's like, maybe we're going to have to do this so that I do it like a slide at a time or something crazy like that. So I think we're going to have to try and do that. So I'm just going to put up your first slide, Bob. And when you want me to switch to the second slide, we'll do that. Okay?
Okay, switch to the second slide.
Whatever we have. Okay. So we're going to switch to the second slide, and we're going to try that. Okay.
So that's the second slide. So what I'm doing first is to show experimental results that are published in the literature. And this one is called the Maxwell-Lodge experiment. You can look that up. I give a reference to the paper. These figures that are shown on this slide are from that paper. The paper is called The Maxwell-Lodge Effect, Significance of Electromagnetic Potentials and Classical Theory. Okay, the point of this experiment is that, well, the setup is a very long solenoid. And as you know, outside a very long solenoid with the appropriate shielding, or if the solenoid goes to infinity, there is no magnetic induction field outside the solenoid. But there is a vector potential, A, outside the solenoid. So they wrap a secondary circuit, or just a coil of wire around that solenoid, attach it to a voltmeter, and when they oscillate the current slowly, see the paper for all the details, there's an induced EMF measured in that voltmeter, or by the voltmeter. And they're saying there is no magnetic induction field outside where that wire is, but there is a vector potential, and it's the vector potential that is causing an EMF to be measured. Okay, so the experimental result, not my interpretation, but those of the author, is that there's an oscillating, curl-free vector potential outside that solenoid, and that's what's generating the oscillating EMF that's being measured. Franklin, if we go to the next slide, please.
Okay, I'm going to switch to the next slide here. So you're not seeing it switching, right?
That's correct. I'm not seeing it switching.
Okay, well, we have ways around that. Okay, now you can see the third screen.
Yes, I can see the third slide. Thank you. The second experiment, which I call the Diabo experiment, it's from a paper from Diabo and other researchers, and it's called Vector Potential Coil and Transformer, published in the IEEE Transaction on Magnetics. And this is a specially wound solenoid. He calls it a transformer. He uses like a spring wire to do the primary winding. It's a little bit hard to describe, particularly if you can't see this figure in detail. So I'm not going to try to really get into all the details of the experiment, other than to say it's a special transformer. It's made by using a spring wire wrapped around a hollow cylinder, and then a secondary wire is run through that hollow cylinder and attached, let me see, an AC current applied to that spring wire in oscillating AC current. They measure a induced voltage in the secondary wire. Within the cylinder, they claim that there is no magnetic induction function or magnetic field within the cylinder. So their conclusion is that there is a oscillating, curl-free vector potential within the cylinder, which is again inducing the EMF in that wire. So there's two experiments now where the authors of those experiments are claiming a curl-free vector potential that is oscillating and causing an induced EMF. Next slide.
How is that any different than standard transformer theory? I mean, that's exactly what transformers do.
But transformers are using the magnetic induction field. Here, they are measuring and from theory saying that because of the special way this is wound, there is no magnetic field. It's all vector potential. And because the vector potential is curl-free, what's the definition of the magnetic induction field? The curl of the vector potential. They're saying their experiments are showing curl-free. Therefore, B, that magnetic vector potential, is equal to 0, because the curl of the vector potential is equal to 0. That's not me. That's the authors of the paper. And they try to measure a magnetic field. They try to measure that magnetic field, and there isn't any. It's 0. For example, take that long solenoid. Theory says outside that long solenoid in that first experiment, there is no magnetic field. There is a vector potential.
What do you mean by vector potential? What is a vector potential?
Go to the next slide.
Okay, let's go to the next slide.
Thank you for doing this, Franklin.
Let's see here. Next slide. All right.
Right, so hang on, I gotta, let's see. So the experimental conditions, in addition to the experimental result, just the conditions of the setup is that they're using regular conductive wires and therefore charge-free, and therefore there is no gradient of the scalar potential function. So the gradient of the scalar is equal to 0, and there's no current density at the secondary wires, the wires that they're using to measure the induced EMF. So the current density is 0. We go to the next slide, please. You're going to love the next slide, Franklin.
Looks like Greek to me.
I know. So here's the experimental results written in math, where the authors are claiming an oscillating vector potential. The vector potential is labeled here as the vector A. Okay, so it's oscillating. That means it's not 0. They're saying that there's a curl-free vector potential. That means the curl of the vector potential is equal to 0. And if you look at the definition of what a magnetic field, magnetic induction field is, the B, that's defined to be the curl of the vector potential. So there is no magnetic field, magnetic induction field in these two experiments. That's why these two experiments are very unique. However, they do measure an EMF in that secondary wire with a voltmeter. And here's the definition of EMF in math. And the conclusion is that they're measuring an oscillating EMF, that is an oscillating voltage. And so it's the time derivative of EMF. They're measuring that, and therefore at the very end, the last line there, the time derivative of E is not equal to 0. That's because there is indeed an induced EMF, and so it's oscillating, and so that is not 0. So if we go
what is E in that equation?
What's that?
What is E in that equation?
The electric field
The electric field.
in the secondary, which is inducing that voltage that they are measuring. So you can see in the line just above there that the time derivative of EMF is equal to the integration of the time derivative of E, the electric field, dot dl. dl, that integration is a path integration around the wire where the voltmeter is attached. So it's the induced E, the induced electric field.
Well, why would there be an electric field? I mean, the wire itself, as long as the current is flowing, is electrically neutral. I would not suspect that there is any significant electric field emanating from any of the wires.
It's the induced electric field. So if you go to the middle equation just before the line with the time derivative, the equation just above that, it says that EMF is equal to the integration of E dot dl. Well, what is E? In Maxwell's equations, E is defined to be minus the gradient of the scalar potential minus the time derivative of the vector potential. And so they're saying, where does this EMF come from? It's coming from that time derivative of A, the time derivative of the vector potential.
And you should probably explain what is A.
A is the vector potential.
And what does that mean? Because most people, that doesn't mean anything to anybody.
Okay, I'm sorry. I'm assuming that, I guess I'm talking like people have had Maxwell's electrodynamics.
Yeah, that would be a bad assumption. So
well,
for our audience who may not know about this, to explain what these things are.
So I guess we should just then go to the next slide. I'll wrap it up and say, well, there it is. I'm sorry I can't really explain beyond, just assuming that you know a little something about Maxwell's electrodynamics.
Okay, let's see here. We are in, okay, here we go. There's a
Okay,
six-
so one of Maxwell's four differential equations is called Ampere-Maxwell law. There's other names for it, and that's the curl of the B field, the magnetic field, is equal to the current density function plus the time derivative of the electric field. Okay, but we've shown, the experimentalists have shown, that the curl of the magnetic field is equal to 0 because the curl of the vector potential is 0, and the current density is equal to 0. Therefore, the time derivative of E, just from that equation, is equal to 0. You go to the next slide. It's the final slide, so hang in there. So now, from Maxwell's equation, we have that the time derivative of E, the electric field, is equal to 0. However, previous slide from the experimental results showed that the time derivative of E is not equal to 0. So the experiments are showing that the time derivative of the electric field E is not equal to 0. However, using the results of the experiment, a oscillating curl-free vector potential, Maxwell's equation gives you that the time derivative of E is equal to 0. That's a contradiction. Therefore, Maxwell's electrodynamics is experimentally proven to be wrong. And it's proven to be wrong because the experiments say the time derivative of this E is not equal to 0. Maxwell theory says the time derivative of E is equal to 0. Contradiction. And when you have a contradiction between experiment and theory, theory loses always. Well, thanks for doing this for me, Franklin. I want to just get the information out there, see if anybody has questions, start a discussion on this. And sorry if it's, just way out in the boonies and nobody understands it. But thanks for the time and for flipping all the slides for me, Franklin. That was great.
Okay, well, most certainly I have some questions. So let's just go back to this Maxwell logic experiment. Let's put that slide up here.
I do see somebody's question. Are you Bob Gray from Ithaca, New York? No, I'm the Bob Gray from Rochester, New York.
Let's see here. So, so you were able to see that chat comment?
I am able to see the live comments.
Oh, cool. So let's see here. Yeah, so if you have some questions, please, if you're on the live stream, please type them in. Looks like we have Bill Lucas here. He's coming in as Rich Otero. Okay, great. So if you have some questions, but I'll get the discussion started with this experiment here. So you can see the Maxwell logic experiment on your screen, right?
Yes.
So this seems pretty simple. So you just have a very, very large solenoid and a single loop of wire is wrapped around it.
That's essentially it. And then they put in a lot of shielding because the theory says that the solenoid should go to infinity. And of course, we can't physically do that. So as the authors of the paper argue and talk about, discuss, they put additional shielding around to make it effectively going, act like it was going to infinity, which means that there's no magnetic field outside the solenoid. And that's their argument. I can't argue that that's true, false, or is good enough for shielding wise. I'm just taking their reported results in the literature and their interpretation and using that.
Well, that's the part I don't understand, because if you have a solenoid and you're putting electricity through it, then most definitely you cannot shield the magnetic field that thing creates. magnetic fields are notoriously difficult to shield. And just from this picture here, it just looks like the wire on the outside is just being hung around the solenoid. And to me, that looks like a regular transformer. I mean, there's no difference between that and a regular transformer. I mean, other than a regular transformer, they would put in like an iron core, but that is the basic way a transformer is constructed, is that you have a spool and you wrap an inner spool, and then you have another spool on the outside, right on the outside of it. And when you vary the voltage from one of the spools, it induces a voltage in the other spool. So what I'm questioning in this experiment here is, how is this any different than a standard transformer? Just looking at the picture here, I don't see it as being anything different than the standard transformer. So I don't know. I mean, I guess I'm skeptical about the author's claim that shields the wire. I mean, I would think maybe if they stuck like a metal sheet between the outside wire and the inside coil or something that different, but they only look like they have air between the two coils. So that's certainly not shielding.
There are other images in the paper that shows the shielding. I didn't select that particular picture to show. I didn't think it was any more descriptive than this one that you can really see the coil. But theory, as I say, the theory of this, it's in Griffiths, Jackson, all the electrodynamics books, says that if you have a solenoid that goes to infinity, then there is no magnetic induction field outside the solenoid, but there is a vector potential. And then how they experimentally justify, well, okay, it's only a finite length solenoid that we're using, and we can shield against the magnetic induction. I don't know the details.
Let me see here. Let me try and share a screenshot of a web page and see whether that displays dynamically or not.
Okay, so there's a question, does this version of Maxwell's equations include Lenz's law and Lorentz law? This is the standard electrodynamics found in Jackson, Griffiths, etc. Standard 4 differential equations of Maxwell's, so-called Maxwell's system for electrodynamics. And so that Ampere-Maxwell equation that I showed is just look at the back of the book of Griffiths, Jackson, or any others, and you'll see Ampere-Maxwell law, sometimes just called Ampere's law, with Maxwell's displacement current added to it. So I don't know if that answers the question. It's not anything different than what's in the standard textbooks.
How about this? Stefan says that the resolution of this has already been made by Hively Vanderlyn.
Yes, I know it, their work. And in a paper that's not published in a scientific journal, but I've made it available on ResearchGate, I have shown that the Hively called extended electrodynamics suffers the same problem, as well as other electrodynamic theories based on Maxwell's equations. In Hively's case, as I say, it suffers the same contradiction. And I've shown that in a paper, as I say, out on ResearchGate. What else do I want to say? That Hively introduces a new scalar potential, which he labels C, the letter C. And under these experimental conditions, that C just reduces to a time derivative of the vector potential. And when he modifies the Ampere-Maxwell equation that I'm using to include C, his C, the new scalar potential, that also drops out because it's a gradient that he's taking in that equation. And you're left with the usual Ampere-Maxwell equation. So adding his C in extended electrodynamics for the Maxwell Lodge experiment adds nothing. And he still gets a contradiction in the end. What else can I say about that? Okay, for the Maxwell Lodge experiment, I did not put as one of their one of their results is that the divergence of the vector potential is also 0. So in the Maxwell Lodge equation, the divergence of A is equal to 0, the curl of A is equal to 0. And it's because the divergence of A is equal to 0 that the scalar function that Hively introduces, C, goes to 0 as well. And so you're left with the usual Ampere-Maxwell law, and you get the same contradiction. You did not include scalar wave experiments. Don't know about scalar wave experiments. The intent here is to show that there are experimental evidence that shows Maxwell's electrodynamics and other electrodynamics is wrong. It leads to contradictions. Okay, then it claims that there are no monopole magnetics which do exist. That's correct. The Maxwell, standard Maxwell, with the divergence of B equal to 0, implies no magnetic monopole. And yes, there are some experiments that suggest magnetic monopoles. You may want to express that a little more strongly, that not just suggest, but they actually do exist. I question that because I'm not finding these as standalone magnetic monopoles. They seem to be within a particular material. They can do some alignment of magnetic moments, and so within a small volume, within that material, they're claiming it acts as if it's a magnetic monopole. Those are the papers that I've seen on it. I don't know if you are referring to other experiments that have standalone particles that are magnetic monopoles. I haven't seen those.
So, and Bill, if you want to participate in the audio conference, we would invite you to go to live.naturalphilosophy.org and go into our little green room, and you can get on and speak. And I notice we do have some other people who are in our little green room, and if you would like to speak, put up your video or send a private chat, and we'll get you on the show here. Let's see, do we have some more questions? Now, I was wondering. Now I've shared my screen differently. Can you see it change slides now?
Yes, something just happened.
So now it says
to another one,
and now we can go back to the Greek slide here.
Yep.
Okay, good. Apparently, if I share my entire screen and not just the application, then it gets the correct results. What if I go to full slideshow mode here? Okay. Do you see the first screen?
Yes.
And then second screen?
Yes.
Okay, so good. So
at the bottom of the screen, I'm also seeing a red circle with a white triangle. It says Richard Terrell. Okay, then it claims that there are no monopole magnets which do exist, and it's hiding the bottom part of the slides.
Oh, that would be, so the comments are kind of covering up the bottom part of the slide. Mm-hmm.
Yeah.
Okay, and that's interesting that it comes on automatically like that. Let's see here. So I guess I have to go back and see the main StreamYard view. So I can hide that is what I can do.
Let's see.
Let's see, we got another question here, which is, what is the name of your paper?
Yeah, I'm getting to that. I got to look it up myself.
Yeah, there we go.
Okay, the name of the paper which I put out on ResearchGate is Experimental Disproof of Maxwell and Related Theories of Classical Electrodynamics. You'll see that the author is anonymous. I put that on virtually everything that I publish. The reason for that is everybody seems to ask me why I do it, so I'll just tell you out up front. The reason why I do it is because I feel that who said it is not important. What I want you to focus on is what is said. That's important. I don't care when I look at papers, I don't care who wrote it, and I hope you don't either. Don't judge the paper based on, hey, Bob Gray wrote this paper. No. Please judge the paper on its content. And if you find a mistake or there's something wrong with the paper, let me know. I will change it.
Although that kind of contradicts like the entire.
Oh, by the way,
for mainstream, I guess, because mainstream is like publish or perish. It's like your name is like everything. So
yes, but I'm not in academia, fortunately. The rest of the question, pardon me, I'm switching around a little. What is name of your paper? I just answered. Did you review Hively patent that describes experiment? Yes. In this paper, Experimental Disproof of Maxwell and Related Theories of Classical Electrodynamics, I use Hively's extended electrodynamics specifically as yet another example where this contradiction occurs. I should clarify, I don't use his patent, I use the papers that he has published.
okay, let's see here. I'm going to go back and see here. So we have some wiki articles here on the Maxwell Lodge effect. Although this paper would be directly saying that Maxwell's equations are contradicted by this. Someone also mentioned the Aharonov-Bohm effect here. Let's have a look at that.
That's right. The Aharonov-Bohm effect, I think, is related to this, but the Aharonov-Bohm effect is in the quantum realm, using coherent electron beams. But I think it's essentially the same thing. They split the electron beams. One half goes clockwise around the solenoid, the other counterclockwise around the solenoid. They bring them back together. They see an interference pattern. Therefore, they think that there's some kind of force or something acting on the two split beams going around the solenoids in different directions. The force on those is different depending on how you go around the solenoid. And I think that's, again, a vector potential effect, but it's in the quantum realm, and so I don't know really what to say about it up at the classical realm, but it's an interesting connection.
Well, I mean, it seems to be your main point here is that these experiments generate situations for which there should be no magnetic field per se. That's typically signified by B in these equations.
Right.
So they're saying that the B field would be zero. Although, like I said, my main objection to this is that all solenoids will have a B field around them. That's like if you've got a wire and if there's current running through it, then B field would have to be non-zero.
You would think, but the quote-unquote experts say something different.
Well, see, I don't pay any attention to experts. I pay attention to my own experiences when I wrap a coil and I put electricity through it. That makes a magnet. Is what that's how you make electromagnets. So I don't possibly see how anyone could say that the magnetic field around a coil is zero. I just don't see how that's possible. So as an investigator, I would certainly investigate that. You should be able to explain that and not take that for granted, really. So I'm not sure whether you're taking that for granted or whether you were convinced that conclusion was correct.
For this presentation, yes, I am taking that for granted. That and the second experiment, the Dabo experiment, because both are quote-unquote the experts in their experiment, and both are claiming the same thing, curl-free oscillating vector potential. And if that's ever physically actually true, that leads to a contradiction in Maxwell's electrodynamics. And that's the point I'm trying to bring out. So I have, from that point of view, I have no, I don't know, really anything to say about if the experiments are correct or not correct, or if there's a leakage of magnetic field, or if there's a... I'm just taking it at face value and saying this leads to a conclusion that Maxwell's electrodynamics is not correct.
Well, I suppose there's like a chain of evidence you have to consider, right? And a break in any part of that chain would be fatal. So if any part that you're taking, just on face value, and you can't justify that chain, then that's where it's breaking for me.
Yep.
Because I see
Although,
that.
as I say, with the Diablo experiment, they put in a lot of little coils, pickup coils, within their bigger system to try to measure a magnetic field, an oscillating magnetic field. They can't measure any. They say it's below what their equipment has ability to pick up an oscillating magnetic field. So they're claiming experimentally they're measuring no magnetic field. By the way, Franklin, I see that it's 11 o'clock. I've taken up an awful lot of time on this, and I don't want to hog the whole session. So feel free to switch to other topics, or if somebody else has anything else. I've said about all I can say, I guess. Thank you very much.
Yeah, but I love discussing the magnetic field. So, and and I'm glad that you brought it up. But if someone else does have a topic, then please let me know. We'll put it on. But I'm still interested in talking about this this particular subject. So I would agree that if they actually just, I don't care about the mathematical chalkboard equation things, because that's not real. But if you take a magnetic sensor and you place it around your experiment and it measures zero, then I would be willing to believe that, right? Because equations on chalkboards is one thing, but it always has to be backed up with experiments. So I'm presuming if that's true, then I really don't care what the chalkboard experiments say. If there's no measurable magnetic field, but yet there's an EMF still being generated, then that is the interesting thing. And I would say that generally contradicts what we think, which is that varying magnetic fields generate the EMF. I mean, that's the basic fundamental thing that Maxwell's saying, right? That variable
magnetic fields generate EMF.
You might be interested in these papers. As I said, I gave the references in those slides. They're interesting experimental kind of papers, and you might, find something of interest there, being experimentally oriented. Yeah, check them out. The other thing I'll say is it's not only an oscillating magnetic field. If you look at, in Maxwell's equations, the definition of the electric field, I have that on one of the slides. The definition of the electric field is a minus gradient of a scalar field minus the time derivative of a vector potential A. And it's that component which is causing the induced EMF right there. The third line down, I have the integration of E dot dl is equal to the integration of the definition of E minus the gradient of phi minus the time derivative of A. That time derivative of A is not a magnetic field. It's the vector potential field. And that's what's inducing these EMFs in these two experiments.
So, I mean, is this like related to the Weber dynamics, where the electric field is the thing that's doing everything?
Yes-ish, in that Weber electrodynamics does not suffer from this problem. Weber electrodynamics uses the Coulomb field rather than this general E field in the Ampere-Maxwell equation, and so it does not have this contradiction.
So what exactly are you showing on this page? I mean, this is a derivation predicting that there will be an EMF?
On this page, I'm showing the experimental results at the top written in mathematics language. The time derivative of A is not equal to 0. And I'm showing because that is not equal to 0, this electric field, time derivative of E, is not equal to 0. That's all I'm trying to show there. From the experimental results, we know that the time derivative of E is not equal to 0. And that's what they're measuring. They're measuring an oscillating EMF in the experiments.
So it kind of sounds like that there just may be some other force, non-magnetic, that can generate the EMF. Is that what you might conclude?
Yes.
So what could that be?
Well, the other thing that generates EMF is an oscillating vector potential.
No, that doesn't make any sense to me. What do you mean by oscillating vector potential? Vector potentials, I mean, a vector is a mathematical concept where it's like an arrow and you point it in space and it has a length and a distance. And so that's a vector. And you put that together with potential, and it's like you have to be potential of what? You have like,
yeah,
have gravity fields, you got electric fields. What do you mean by vector potential?
Okay, the vector potential is related to the current density function. So if you have a current, you have a current density function, a current per volume.
Yeah.
And so you can write this A in terms of the current density function. So here you have a time derivative of A, which means you're going to have a time derivative of the current density function. So you're oscillating the current, and it's that oscillating current that's causing this EMF.
Well, I can get current, okay. Now, as far as what A is concerned, I understand that A is basically the curl of B.
No, B is the curl of A.
Okay, B is the curl of A. Now,
A is the integration of the current density over the distance away your test particle is from that current density. So it's an integration of the current density.
Well, my understanding is that basically since
B is the curl of A, that A is basically perpendicular to, say, B at any given moment. And in my experience, it generally represents the vector direction flow of the current that's causing the magnetic field.
That's correct.
So really, A is just the direction of the current.
That's correct.
Which is, why don't people just say that, right? That's a lot easier to understand.
Oh, come on.
Rather than vector potential and blah, blah, blah.
We got to look like we really know something.
Me personally, I think that the magnetic field should be defined as A, and we should do all our math in terms of A, because that's the thing that's causing the magnetic field in the first place. Right. So we should pay attention to that direction and not some made-up direction we come up with as the curl of that, right?
Yep. Yep. Well, I'm really into Weber electrodynamics, and I've probably said this several times, but in Weber electrodynamics, there is no magnetic field. There's only the Coulomb field. But we don't need to divert into that. There's another question here. Talk about longitudinal electrodynamics waves, which also contradicts Maxwell's equations. Okay.
Well,
I did a presentation at a conference in Albuquerque about a month ago now, where I talk about longitudinal waves, and it was really focused on Weber electrodynamics. In Weber electrodynamics, there is only longitudinal waves, but when you add, okay, so each discrete charge body generates a longitudinal wave. When you have lots of discrete charge bodies moving together, for example, in currents, or even just two to make up a dipole, the way that the fields add gives you a transverse component. And so my hypothesis is that the reason in the experiments we're getting into a lot of transverse wave stuff is because the sum of these longitudinal waves is giving a transverse component. However, fundamentally, there is only longitudinal waves. That's the point of view from Weber, my version of Weber electrodynamics. And aside from that, yes, I would agree that the derivation of Maxwell's equation is really screwed up. The derivation of the wave equation from Maxwell's electrodynamics is really messed up. It's not correct. And the interpretation from that there's only transverse waves, is just not correct. And I had that, as I say, in another presentation.
Yeah, I totally agree. Amen. Okay, that's that has been one of my things about that. I think that that we should treat the magnetic wave as an ordinary wave, which is mediated in a particulate medium, and those are not transverse waves; those are ordinary type compression waves. And like everything you said, Bob, that I think that's absolutely true. So, so I see Dennis. I see your video. Did you want to speak? Wave to me if you want to speak. Okay, I'm going to put on Dennis here. Go ahead, Dennis.
Remember, I sent you a book on vector vector
I got that book.
operators.
Yeah, some time ago.
This book. Haven't quite gotten into it yet.
Oh, I see. Well, the thing is, he's right. The A field is more fundamental than the B field because B is equal to curl A, but the curl is not one-to-one. It doesn't separate points. You lose information when you take the curl. So to use B instead of A is to throw away all that extra information. Now, people nowadays think that that's all right. The extra information is not valuable, but it is valuable. And so I thought I'd send you that book so you could, brush up a little bit on this sort of, because you need to know that as a minimum to be able to really understand what was being said just before I talked. That's, it's just you can't, it's like trying to understand accounting without knowing how to add and subtract. Or multiply and divide. It's just not possible. So, if you hold that book up again, I'd recommend that book to anyone who is interested. That's an older edition, which is all I could afford used too. But I thought I'd send it to Franklin because he can now show it to everybody. And yes, the A field is the basic thing, although J.P. Wesley goes back even further than that in his book Scientific Physics. And he has even more fundamental potentials that he introduces. And I don't agree 100% with his approach, but it seems to be better than any other one I've run across. It's one of those things. And he has chapters 4, 5, and 8, I believe, on this. And he shows things like the Biot and Savart law is not correct unless you're just dealing with two rigid circuits. And so the Lorentz law of force is wrong too, because it doesn't conserve energy when you have a charged particle, which is whose magnitude of its acceleration is increasing, for example, not the direction, but the magnitude isn't changing, then the Lorentz law of force on that particle does not conserve energy. So, I urge everyone to get a copy of that book if you can afford it. It's $55 plus $4 shipping and handling from his widow, Wesley's widow in Germany. And so that's all I wanted to say.
Wesley's work is phenomenal. I really like it. I have his books. And his son has somewhat recently, a few years now, I think, put up a web page on his father's works.
Yes.
So I don't know if the son here in the United States is selling the books as well, or if you still have to go to Germany to get them. I found some are available at some universities so that you can get the books through what's called interlibrary loan. You go to your public library, they can get books from any library in the world virtually, and let you take them out for a week or two. So it's available, but you got to do the work to get them.
Yes, and the binding is trash binding.
Yeah.
Every one of the pages falls out. You have to keep a rubber band around it.
Absolutely. Yep.
All right. Well, Dennis, that's very interesting that you think that the A field actually contains more information.
Well, it definitely does. The question is, does it contain more valuable information? It definitely contains more information because the curl operator is not one-to-one. Two different vectors, fields, if you apply the curl to them, can equal the same vector field after you take the curl. So you lose information. There's no question about it. But people nowadays say, yes, that's right, but we don't care about that information. It's no good to anybody.
Well, it seems like the B field is more complicated than the A field. So if I have a straight wire, so the A field would basically be running parallel to the wire.
Yeah.
But the B field, they show, is actually a circle around the wire. And
yeah.
So So what information are
and
you
the
losing
then
by
you've got all
doing
these
that?
right hand and left hand rules, and
Yeah,
I
all
mean,
that.
it's A field is so much nicer.
Yeah, I feel that this whole cross product thing, because anytime you deal with the magnetic field, you have to
Yeah.
deal with this cross product thing, which is really a mind bending kind of, you
Yeah,
know,
it's hard
spin
to
out your fingers
visualize.
and stuff like that. But if you were to just think of just using the A field, like figure out, say, the Lorentz force law, then you would just say that the charge is deflected in the direction of the of the electric current, right? Same direction, actually,
Yeah,
right?
yeah.
It just seemed a lot simpler to visualize the effect of the magnetic field as like, I mean, you could literally think of the electrons in the wires being like a river, and you throw a leaf in the river and the leaf goes downstream, right? That makes a
Exactly.
lot more sense than you throwing a leaf at a fan and it goes up, right? It goes at 90-degree angles to the thing that you think you're measuring against.
Well, it's for historical reasons. Just like, Benjamin Franklin said, well, I'll say the current flows from positive to negative, but it turned out they flowed from negative to positive. But it was too
Yeah,
late by the time they found that out. And so, it confuses every freshman physics major. Why doesn't the current and the electron flow in the same direction? I mean, if the electrons are the current, why doesn't the current flow in the same direction as the electrons? Well, Benjamin Franklin guessed wrong, that's why. And now it's too late. It's the same with the B field over the A field. Everyone knows the B field because it's the Earth's magnetic pole. If you have a compass, you can't use the A field to figure out without a lot of difficulty which direction is north. You use the B field. So it's convenient.
Yeah, the A field would be like a solenoid thing if you were to figure that out. Because,
Well,
like I said,
yeah,
the
A field, if you had an A field detector, it'd be hard to find out which direction was north. Harder, at least, than, if a B field, we know what direction is north because a magnetized compass needle points north.
Yeah, I think that the B field was defined primarily as a response to what they see iron filings do.
Yes, exactly. That's it.
Which is what, compasses do. So they see that, around the magnet, you get these, fields that look like that. And they decided, okay, that is the magnetic field. We'll draw the lines that way.
Yeah.
Although you can draw the lines, in the solenoid fashion. It's like a topographical map. It just represents regions of equal potential, right? So there's equal potential this way, or there's also equal potential around the axes as well. And it was just a matter of what they were going to pick to represent that. And by convention, because that's what we see magnetic filings do, we decided to define the B field in that direction.
Yeah.
Now, one of the things I've been trying to think about and try and derive is like doing something like deriving the Lorentz force law in terms of A and not in terms of B. Has somebody done that? I mean, I don't think.
Yeah, well, B is curl A, so you just substitute curl A for B.
But what does that mean? It's like, how do you, I mean, the curl operator would have to take the place of the the cross operator, which is yet another crazy thing. I'm thinking that ideally you should be able to derive the Lorentz force law in a way that doesn't have to use the cross product.
Franklin, the Lorentz force law does not conserve energy in the case where the charged particle's magnitude of its acceleration is changing.
So the Lorentz force law doesn't exactly apply for an accelerating particle?
Not unless it's the magnitude of its acceleration is the same all through the trajectory.
Uh-huh.
It's my understanding that the force law it was derived using an integration around circuits.
Yeah,
And
the Biot-Savart law. Yeah,
it's really only valid for closed circuits. It's
that's
not
right.
valid for discrete charged bodies or particles, if you want to say particles. It's not valid for that.
No, no, it's not. But everyone thinks it is. I mean, it's so frustrating. You know, you can't get to first base talking with anybody. Yeah.
Well, see, we just have to get everyone to pay attention to the A field rather than the B field. And then our intuitive concepts of how the magnetic field work will be a little bit clearer, maybe. Although getting back to what Bob was showing is that so Bob is showing that if there is no magnetic field, the EMF can still be generated.
Because,
And
yeah,
that's
take
interesting.
the
I'm not
take
sure
the-
what it is.
take the Hooper-Monstein experiment, for example. You have two cylindrical permanent magnets magnetized in the usual way, and you turn one upside down, and then you approach a wire symmetrically, except that the one magnet is upside down. There can't be any B field on the wire because the magnets oppose each other, yet a strong current is induced.
Well, that's an interesting concept. So you get the magnets that they essentially null out their field.
No B field, but there is an A field because the B fields cancel, but the A fields add in a situation like that.
So if you were to stick like a magnetic sensor between those two magnets, it wouldn't necessarily measure a magnetic field. But as you move those magnets past the wire, they would generate significant EMF.
There's no B field on the wire due to the geometry of the situation. You have two cylindrical magnets approaching the wire in the middle, but one is upside down. That means that the B fields cancel at the wire.
Yeah, but we're kind of saying that there is actually no B field. That B field is just
Well,
an imagination.
what do you mean no B field? If it cancels, how can you experimentally tell the difference between no B field and a canceling B field? You know, that cancels to
apparently
zero.
you can't. I mean, if the B field was just an imagination in our minds because we made a big gigantic mistake, and if it's actually the A field that we need to be paying attention to, maybe that would be an example of where you lose information, right?
Yes.
Where theoretically the B field should be canceling, but actually the B field doesn't actually exist at all. The only thing that exists is really the A field.
Well,
moving at a 90-degree angle.
What do you mean by exists? You can measure it.
Well, if you have a theory of magnetism, which I do, then you could say it has a specific realization. So my preferred embodiment of the magnetic field is that I believe that space is filled with these dipoles made out of positrons, electrons. So that in itself is like a little magnet, right? So if you have those dipoles, then that dipole field can, if you line them all up, because normally in space the dipoles are all randomly oriented, right?
Yeah.
But if you line them up in one direction, then that forms a vector direction.
Yeah.
And that would be your A field. So as you move current through a wire, my hypothesis is that combs the random dipoles from being randomly oriented to being polarized basically in one direction. And so that is what I think is a magnetic field. So that's how I physically realize a magnetic field.
You know, Paul Dirac did the same thing. He was the one who came up with the original positive electron, negative electron space, well, ether, you might call it. That was
that's
Paul
exactly
Dirac.
my feeling is that, and it's not a very uncommon thing. Means several people have proposed that space is actually a positron electron sea of some sort, right?
Yeah.
It's like Mahoney thinks that it's a solid crystal matrix modeled after like salt. I think it's more like a fluid, so that it can so it can orient itself and it can be polarized. See, if it was a salt, then it would be mandatorily already polarized, and then what would a magnetic field be in that? Right? It's already, it can't move. It can't represent the different directions. So that's why. But we both think that it's a positron electron C, because if you take because you can inject positrons electrons from what looks like a vacuum, right?
Yeah.
And it's either you believe that there's something magical where gamma rays can turn into matter, or I think it's more reasonable to think that there was just a neutral particle there before, which you just used energy to split. Mm-hmm. So that in itself, to me, is pretty good evidence that that space is filled with this positron electron C, and it serves as the medium to create the magnetic field. So we're trying to figure out, what kind of thing explains all the things we observe. So and magnetic field is certainly one of the things that we observe. So physically, we do have to come up with some kind of explanation. So, but you asked, how, what would the magnetic field actually be? The magnetic field would actually be this polarized alignment of dipoles. And if you think about it, then when a charge tries to go and cut through those aligned dipoles, there'll be positive in one end and negative in the other. And so you put a negative charge through there, it's going to be repelled by the positive charge as it goes through. So it will deflect as it cuts through those layers of dipoles. And that's why that's the actual basic reason for the force existing, and that it's actually an electrostatic force, in my opinion. And this is why an electric field will only act on a moving charge. Because if you put a moving charge in this dipole field, it's not going to do anything. It's just going to might be like slightly attracted to the closest positive charge, but otherwise it will not be deflected anyway. And that is one of the hardest things to explain about the magnetic field, that it only acts if the charge is moving. And I would say that's the reason for that is because it has to physically cut through layers of dipoles in order to get deflected from layer to layer to layer to layer to layer. So that to me makes more sense. Well, what do you think of that, Kenneth? If you haven't heard about a physical theory explaining the magnetic field, because that's what this is. It's a physical theory explaining the magnetic field.
Well, that's if you can visualize things better that way, then that's the way to go. We're not likely to ever really know the answer to that because those things are so small, but you can't view them or anything. But so the thing is to follow Newton's advice. He said all of physical philosophy basically boils down to figuring out certain key phenomena and then using your results to predict a whole bunch of other phenomena. So, and Newton had a black box theory. He didn't know what force was. He said that it's just one of his undefined terms. Everyone knows what it means, sort of thing. But Newton had a black box theory. He didn't explain what mass was either, but he explained inertia, which is resistance to force that mass has, in terms of just that, resistance to force. He defined things by their effects rather than their causes. So any effect that turned up later would fit into his scheme.
But those are kind of like functional definitions and not really explanations of what, say, mass is.
No, they're not. But the idea is that you can send ships to the moon. You can build all kinds of gadgets that are extremely handy. You know, you don't have to know what the electric field is or what the gravitational field is or what inertia is or what mass is. You just have to be able to predict things so you can get things done.
Let's see. Now we have a couple of questions here. So let's go over that. So we have Cornelius here. How about this? Longitudinal waves are the basis for gravity and mass. It is the interference of two or more longitudinal waves that produce the transverse electromagnetic waves of electrodynamics. Now, I don't know if that's even remotely true. Most people, for example, don't believe that longitudinal waves are the basis of anything in electrodynamics. I would personally believe that longitudinal waves are the basis for all these things because I think that only longitudinal waves can exist, right? I don't believe that, as Bob was saying, that transverse waves actually exist. But I would agree that that the interference of two longitudinal waves create forces and not the transverse electromagnetic wave of electrodynamics. And actually, I think even in the mainstream electrodynamics, it's not really an interference, but more of a cooperation between the magnetic field and the electric field. But I still don't even understand that because in like the experiments and Maxwell's equations show that these fields are induced from one another. So if you have a magnetic field and it's rising, then that will cause a trailing electric field, right? It's the magnetic and electric field should be 90 degrees out of phase, but in all the pictures, they're shown to be 100% in phase. So that as the magnetic field rises, the electric field rises in exactly the same time. And that is something that contradicts also Maxwell's equations.
Well, according to Jeff Kamenko, electric fields don't generate magnetic fields, nor the other way around. He says that they're both causes of a one single effect. I don't believe that's true, but you know he was a very brilliant man, and his books are very interesting. I find.
Let's see. Here's another question here. So does anybody know about this? Can you talk about Grenade, Day, Nikolaev, and Stefan Marnoff and scalar magnetic field? Does anybody know about that?
Stephen Marinoff experiment is explained in Wesley's Scientific Physics in either chapters 4 or 5, I forget which, as A-field phenomena. If you use the A-field correctly, you can get the correct equations to govern the Marinoff motor, which is, according to Maxwell's electrodynamics, cannot operate, but you can watch it operate on YouTube and stuff like that.
So I think it's interesting that we're kind of coming up with this idea that if you use the A field, you can use it to more accurately predict these magnetic effects. Because the B field, which doesn't actually exist and could theoretically be zeroed out, and like Bob says, these, in theory, magnetic fields are zeroed out, isn't actually the thing that's has any relevance.
The magnetic field is a derivative of the A field, a mathematical concept, which happens, however, to correspond to compasses and iron filings and whatnot, which people believe more than they believe the theory, you know.
Yeah, I think Cornelius has a comment on that we can more easily measure the current from the permanent magnet. So it is more practical to measure the B field in this case. I mean, the B field is the direction that a compass points, and that's a very easy instrument to look at and read, I guess. So yeah, I would agree with that it's just easier to measure that.
I have a paper that, have you ever heard of the Crane-Monstein effect? magnetic effect?
No, what is that?
If you have a cylindrical permanent magnet that's really strong, like it's a boron, niobium, iron one, and if you rotate it on its axis of symmetry, depending on which direction you rotate it, the magnet becomes stronger or weaker. And
when you take a ring and you just like spin it in place so you can't see it really moving?
yeah, I mean, it's spun on its axis of symmetry.
Well, what does that mean by that?
The axis of symmetry of a cylinder is the line that goes through all the circles that make up the cylinder. It's the axis. It's
so you spin it around and it would look like a sphere then, right? If you take a ring and you rotate it around, it would essentially carve out a sphere?
No, it's a cylinder. If you take a cross section, it's a circle, right?
Yeah, it's a circle.
Okay, now consider all possible cross sections that are circular. Now, draw a line through all their centers.
Well, none of that's really making any intuitive sense to me. But okay, so I've got a CD here. Okay, so what does it mean to rotate it about the axis of symmetry?
You rotate it about its center.
Does that mean this?
No, in
or
the
does that mean this?
Yeah.
This means this, like this.
Yeah. And if a cylinder, if you rotate a cylinder, all the circles that make it up are all rotating in the same direction, right?
Yeah. So you're saying that if they spin it, does the magnetic field get stronger or weaker?
Depending on which direction you rotate. There's two directions.
Okay, but that would be like to the north or south, or?
Yeah. If you look at the North Pole and you rotate it either clockwise or counterclockwise, I forget which, relative to the North Pole now, then you get either weaker or stronger, depending on which direction you rotate. Now, this is explained in my, which I actually do direct calculation using that stuff that's in that book that I sent you, because each of the electrons is a circle of charge that's rotating about its center, like that disk he showed just a minute ago.
Mm-hmm.
So the magnetic field is along the axis of symmetry of the electron, but the free electrons and the other electrons too are randomly oriented in general. So there's no magnetic field. But in the case of an iron, niobium, boron magnet, which is extremely strong, the electrons are lined up. They're what makes the magnetic field of the thing. But if you rotate it about its axis of symmetry, then it either becomes weaker or stronger because you're either rotating basically in the same direction as the electrons, or you're rotating in the opposite, basically in the opposite direction of electrons. If you rotate in the same direction, it net increases their circulation. If you rotate in the other direction, it net decreases the circulation. So, and I actually calculated this, and if you're interested, I can send it to you.
Okay, well, I kind of intuitively think that might be true, because what I'm thinking is that in a permanent magnet, there must be current loops inside the magnet of some sort.
Yeah, exactly. Electrons are current loops.
I don't believe, though, that the electron itself, and a single electron itself, has any magnetic field. I believe that there must actually be a superconducting loop of current in there, as if there were a superconductor. And this is kind of, controversial, when saying that a permanent magnet is in fact a room temperature superconductor that has a superconducting electron loop in there, and I think it's looping around the crystal structure that's in the magnet. But if you're saying that, then you could see that maybe if you rotate it one direction, that you would be basically accelerating the current, and you rotate the other way, you would actually be decreasing the effective
Yes,
current
exactly.
in those loops. So, yeah.
But why don't you think an electron is a circle of charge that's rotating and hence generates a magnetic field? I mean, electrons, they do them in vacuum tubes and so on. They know for a fact that the thing has a magnetic moment. I mean, they measure it all the time, like in penning traps and so on.
Well, I would ultimately say, though, that what they're measuring is not actually the magnetic moment. The problem is, if you want to put an electron in motion, then that itself generates the magnetic field, and that I would assert that that is what they're really measuring. But a single electron itself cannot represent a magnetic field and is not, because if you go back to how I thought how the magnetic field is actually mediated, it's like it's mediated in these dipole particles, right? So, and there has to be a whole bunch of them together to create any kind of magnetic field. And if the interaction between the electron itself is only electrostatic. So the only thing the electron can do is emanate just its negative electric field. By itself doesn't have a direction that would represent its magnetic field.
Yeah, well, but here's the problem with that. If you take electron as being a symmetric charged sphere, say, then it explodes unless you have mysterious binding energy keeping it from exploding. Or if you say that it can't explode, I just postulate that.
No, I said, well, this is where you have to explain what the electric field is, okay? Now, in my world, the electric field is just a very high frequency wave that's being emanated by the resonant frequency of the electron. So the electron is like a bell, and you hit it, and it rings at this specific frequency. So this tells you that the electron is not made out of smaller negative charges. The electron is literally a physical bell, and you have to hit it to make it ring. And this is where it gets the energy to constantly create this infinitely ranged electric field. And it works exactly like what we think a light wave would do, right? Because that's what light waves do. They once they're generated, they travel infinite distances, and that is what an electric field. An electric field is actually just a special case of a light field. Basically, it's like every single electron is like a little light bulb, and I believe that the only difference between the positron and electron is that they are out of phase as far as the light that they're emitting, and when the waves come together, if they're opposite, they cancel, and that creates a low pressure area, and that's what actually physically shoves the two particles together. You get two identical particles, then the waves add, and that creates higher pressure, and that's what shoves them apart. So this solves the problem of, why doesn't the electron explode? Because the electron can only explode if it's made out of smaller negative charges, which you still haven't explained. But if I explain that the negative charge is just literally a light field around the electron, then we don't have to worry about explosion. We do have to worry about how the electron generates that field. And I would say that, if you stick your fist inside your bathtub and you start shaking it around, that generates waves. So
yes, but the problem is this: you want to, according to Newton's, what I quoted before about what physics was all about, you want to be able to predict things. Now, considering it as a bell is not real conducive to calculating things like what waveforms, what causes the frequency of the electron, and how would it change under high pressure and intense radiation and so on. You're it's sort of like a little bit, and I don't mean to criticize you, but it's sort of like in the old days. They said, well, the Earth is on a big turtle, and that's why it goes around, and so on. It made sense. Everyone knows what a turtle is in those days. Nowadays, probably they don't. But it's not terribly conducive to calculating things.
No, actually, it is. I mean, this particular idea isn't my own.
I know. I've heard it before. Yeah.
This came up. Some guy experimented with this, 100 years ago. 100 years ago, someone came up with this, and he experimented. And you can show that experimentally, the 1/r² force can be created in even a water and pulsating balloon situation. So physically, you can do that. You can also calculate exactly what goes on. And I believe that, in these papers, they actually mathematically show that you can derive the 1/r² force exactly using this kind of interacting waves thing. So, but in order to do this, you need a particulate medium, and you need something that vibrates, and you need a power source. So the power source is just all these particles bashing into each other all the time. I'm not 100% sure what the mechanism behind the ringing is, other than it's similar to resonant frequency. You take anything and you hit it, it has some kind of resonant frequency, no matter what it is. So that you do have to postulate a couple of things, but at least we're dealing with things that people know about, which is an electron. And it may be possible to actually experimentally measure the super high frequency that comes out of these things if you were to look for it. I mean, this would be the highest frequency possible in the universe. So it'd be really high, but still theoretically possible. But at least we're not dealing with, like, if I made up, something called a circulon or something that no one recognizes, then that would be more difficult. I'm only dealing with, I'd say this is an electron, that's a positron. Everything is made out of electrons and positrons. There are no mystery ghost particles, except for my ether particle, which is like a neutron. So all easily recognizable mainstream particles. So I would think that'd be more advantageous. Now, I see, though, we are getting close to the time here, and I do know that we do have a recent spat of comments here. So let me just look at that here. So Stefan wants to know if Cornelius can give you literature on the basis of gravity and mass based on longitudinal waves, and he says that no paper. So I think that is something that he knows about. And Cornelius is also saying that a magnetic monopole does not exist. It is only mass. I'm not sure if I quite understand that thing. Questing says Darwinian and universal guys. I'm not sure what that means either. But thank you for your comment. But Stefan says that electrodynamics does not describe gravity. So longitudinal electrodynamic field is not connected to gravity unless you have some theory. Now, I would say that gravity is strongly connected with electrodynamics in that simply the gravity is the positive electric field. I mean, it's just as simple as that. The Earth loses electrons because electrons are easily lost, just like when you put your comb through your hair, it becomes charged. Earth becomes charged, not by much, but it becomes a strongly charged positive ball. And the thing that people don't understand is that neutral matter is attracted to any source of charge, right? And so we're just being sucked down to the Earth, being attracted to the positive charge. So in that way, it is, in fact, an electrodynamic field. That would be my 2 cents on that. And Michael and Teskey is saying that they explain the life force being one directional. They existed in hypergenic etheric settings elsewhere than our quantized Earth environs. Well, that seems a little mystical to me. Maybe a little bit more religious, but interesting. See here, another. So space possesses an energy field. Baryons are force fields that consume the energy of the field of space. Baryons evolve from and process processes optimized for exploiting an energy field of space. Well, I would kind of agree with that. I would say that space has energy and that it's a very chaotic collisional thing. Like I said, I essentially fill space with neutrons, and they're constantly colliding with each other. So there's energy there. There's like lots of energy there. And you have to wonder, like when you take a magnet, you stick it on the refrigerator, a lot of people think that it must take energy for it to constantly defy the force of gravity and provide the active force against the refrigerator to do that. And I would say it's true. But I would say that the magnet is extracting the ambient energy field, that field that just makes up the 70-degree temperature of your room is actually quite a bit. It's like every individual molecule is like moving at like 3,000 miles per hour. And at the level of the ether would exist, it's probably even greater. So there is this, I think, a harvestable energy field out there that magnets harvest at least. And that they are literally consuming the energy. I think that if you took a magnet and you took it down to absolute zero and robbed it of all of the thermal energy, that you would find the magnetic field would drop to zero. And in fact, the entire magnet would fall apart because there would be nothing left. You would actually be canceling the Coulomb force by doing that. That's kind of one of my predictions. And it's kind of been shown that that's true, that in these ultra cold experiments, they'll take rubidium atoms and they'll cool them down to absolute zero. And when they heat them back up, some of them just literally disappear, and they just anomalously, they can't find them anymore. And that may be because they literally fell apart and got reabsorbed into the ether. But that's kind of my comment on that. And let's see here. What does David got to say? So energy is a concept. We need to deal with physicality. So actually, I say what energy is not really a concept. I would say that energy is matter in motion is how I typically like to see that. So anytime you see matter in motion, that matter has energy. And the greater the motion, the greater the energy. So I think that is something we can physically deal with. But I do agree that we have to deal with things which are really physical, right? So I'm not sure. Let's see what was Questing proposing. That there is about the being energy. So I think I already tried to explain that a bit. What is this? Can you talk about Tesla scalar waves, which produce different form of electricity, which he called radiant energy? I'm not familiar with Tesla scalar waves. Dennis, are you familiar with that?
Wesley points out in one of his books that you don't need a vector equation for waves. You can use a scalar equation, and it basically describes the same thing only in a different way. He also goes into transverse waves and as well as longitudinal waves, as well as transverse waves. But his theory is complicated because he has no magnetic field, only the A field. And in fact, he goes back to even further than the A field. And also, he died before he could finish up, which is always a bad thing, of course. So, according to Wesley, at least, scalar wave equations are sufficient to describe all the behavior of light, including transverse wave light and longitudinal wave light, where light is more generally, by that's meant electromagnetic radiation.
Mm-hmm. Well, let's go on. Let's see. We've got a number of comments to get through here. So, question is saying, complex systems nested within complex systems. How does nature generate complex, articulated, systematic structures and processes? Design, no. Chance, no. Evolve, yes. Well, I could give a stab on that. See, now I think that the complexity arises, just like in our computers. Fundamentally in our computers, there's a bit in there and it holds a 1 or a 0, right? Now that in itself is not that complicated, but yet we can see here we're in our conference where you can see my face and it looks extremely complicated, right? But all based on the digital ones and zeros. So I believe that the digital ones and zeros of our universe are simply the positron and the electron. So you take positron, electron, the electron stands by its own. I'm not sure why we don't have any positrons, but if you take 2 positrons and 1 electron, that leaves you a particle made out of 3 things, which is charged with +1. Call that a proton. Okay, and then you just take your positron, electron, that is a neutron. Okay. Now, given protons, neutrons, and electrons, we can build a hydrogen atom. And then you take 2 protons, you can build a helium atom, and then so on and so forth. These things glue together until you get something that looks like this. This would be like a gold atom and follow some specific geometric pattern like that. And then once you get all the atoms, then we can build anything that we see, and we wouldn't have to really, go past the mainstream to do that. We just have to originate really just the proton, the neutron, and the electron. Once you do that, you can build everything that we currently observe in the universe. So actually, it's not that complicated. I don't know, it's evolution, though. I mean, our systems may evolve, but the fundamentals, I think, are pretty simple. So Cornelius is saying an electron field does not simply rotate, it precesses as well. That's why it has handedness, as shown by the cross product that's demonstrated when they are linearly accelerated. Like I said, I know about these experiments which tend to show that maybe they have, say, handedness or a spin, like the Stern-Gerlach experiment, but I have a lot of criticisms to those experiments. I mean, if you want to show to me that there's something which is anything other than just a spherical field, that's what it is, then you have to show it to me on a non-moving electron, okay? So if you can show me, you measure handedness on a electron which has been measured in place, not moving, then I might believe you. But I believe all of these experiments, like in penning traps, they oscillate the electron, and it's like, once you do that, you are generating the magnetic field that you observe, right? So it's kind of like, circular reasoning, right? It's like, so unless you can prove that it has these properties in a stationary atom, then I'm not generally believe, but I'm not totally an expert in that. The question says, atoms embedded within an energy of space which exploit for the purposes of generating atomic forces. These forces evolve the complex structures and processes optimized for exploiting space energy. I would generally agree with that the energy of space generates the atomic forces, and that's what glues everything together. And once you can glue together carbon and oxygen and nitrogen, then you can build human beings, right? Now the question is, can we exploit this space energy so that I can charge my cell phone without plugging it in? I should be able to just absorb the ambient space energy. And I think that may be true, that it's not inconceivable that we could generate something that receives the energy, just like a permanent magnet receives the energy, right? And it can constantly defeat the force of gravity forever, right? That's a harvesting of the ambient energy. So if someone wants to do that, please do, so that I don't have to charge my cell phone or charge my car or charge anything and not have to pay the power company a couple $100 to heat my house. That would be great. Okay, just telling you, that's a possibility. So Michael and Tess says, stable orderly quantum systems like atomic structuring require underlying ether dynamic operating through a continuum of linear transmission connecting similar quantum loci. Yeah, generally I would agree with that. I think anyone who's like an etherist, who think that space is filled with something, I think David had a comment that, yeah, we have to think of space as being filled with something. We may disagree on what that particle might be, but this has to be physically something there in the quantum level that's that transmits forces from place to place, so that there's no spooky action at a distance. If everything is filled with like this gas of some particle, then we can explain every A affects B as being a direct linear chain, and there's no magic and mystery there. But then we'd have to believe in an ether, I think. And David says, philosophically, design, chance, or evolve ends up deterministic. And I would say that it is, I would agree, it's deterministic in that people kind of think like evolution is like random, but it absolutely isn't random. It's like if people are going and choosing their mates, they're choosing the best mate and the best characteristics that they want passed on. So that's a choice. That's a decision. People are making decisions when evolution happens, right? It's not like all the random people just mate with random people and everything is chance. It's not chance. It's directly driven by intelligent choice, I would say. That would be my spin on that. Right? And evolution deterministic, yeah, I think you could maybe agreeing with that. But there's always a random drift, and the random drift would be just kind of the random characteristic that might happen to someone. Maybe someone has a particular eye color that just randomly gets introduced, but somehow that becomes the more attractive thing, and that's what people will go to. But you have to have that kind of random drift in order to get any changes in the system, I suppose. So there was something about interacting longitudinal waves. I'm not quite sure what that refers to. So question says, David, I have a detailed set of ideas. They are very well developed and comprehensible, titled Darwinian Universal. So if you would like to present your ideas, you can come here, back to this conference here, and like Bob, we can make you a presenter. And I think we would love to hear what your detailed set of ideas are, right? So if you want to do that, contact me at franklinwho@yahoo.com, and we can get you on the show. And same for anybody, if you have a theory that you would like to have tossed around, we would love to have you. That's what we're here for. So we have life evolves structures and processes formed an agency optimized for exploiting energy potentials, which allows them to exist. Yeah, I guess that's kind of the basis of evolution. And let's see here. The questing think we're taking a lot for granted. Well, maybe. And it's kind of a philosophy of science thing. It's like, what things do you choose to believe as your postulates, and is that fair? And let's see here. So if you would like to, let me see here. Okay. So if you would like to be a presenter on this show, and we're at the end of our time today, and please contact me, franklinwho@yahoo.com. And we're a nice, friendly group of people who are like-minded. And, unlike other places where they might say, we don't believe you because you're not mainstream, right? That you get a lot of that. No, we still may be critical, but we'll pick your idea apart based on, logic and reasoning, and not just because you're not a college professor or you're not Einstein or anything like that. So this is what we're really here for, which is to encourage different kinds of scientific thinking, and just to be a place where people can come and discuss any of their ideas, just like we did today. So in conclusion, I thank Bob for just coming on and presenting his ideas about how the Maxwell equations might not be right. And I think we were kind of come up with this interesting conclusion that the A field, which represents the direction of the electric current, is actually more important than the B field, which is what we measure with, say, compasses, right? And that perhaps we can get more accurate predictions by using the A field rather than using this B field thing. So, but I think that will do it for this week. And let's see here. Yeah, okay. So we should be back here again next week. And hopefully we'll iron out a few more of the kinks here on StreamYard. And make sure to tell all your friends. So bye-bye for now.